Hey guys, welcome back to another A-Level Maths video. This time we're finally starting to go through kind of hard problem-solving exam questions. So again, my students have sent me various questions that they have found difficult, and when I've been writing explanations for them, I found that, yeah, it does require some weird nuance to it, and it's a little bit trickier than the normal question. So this here is a normal distribution question. 14 marks in total is pretty fat, but remember, there's only around 4 or so stats questions and 4 or so mechanics questions in your actual exam, so they are very fat questions. Now, it's part A and part D I don't think are too bad, as long as you know how to do a hypothesis test, and for part A, as long as you know how to do the normal distribution. But part B and C, where you have to use quite a bit of problem-solving techniques. So I'm going to go through that, and well, we're going to see. So for part A, we have the lifetime L hours of a battery has a normal distribution, so we have L approximated by a normal distribution, and has a mean of 18 and a standard deviation of 4, so comma 4 squared. And Alice's calculator requires 4 batteries and will stop working when any one of the batteries reaches the end of its lifetime. This, believe it or not, this is useful information for the later part of the question. For part A, it just says find the probability that any selected battery will last longer than 16 hours. So you're looking for the probability that L is greater than 16. Which, if you're doing that on a normal distribution, is quite nice. You just go to your menu, you find wherever your distributions are. I went too far down. Then you do the normal cumulative distribution, and you enter in your values. Now, the lower value is, of course, where we're starting from, which is 16. The upper value, you just need to enter in a really, really big number. Mu is 18, standard deviation, whoops, got that the wrong way around. Sigma is 4, mu is 18. I could have swore that said mu. And we get 0.6915. I normally give it to 4 or 5 decimal places. It doesn't really matter though, so I'll just give it to 4 decimal places. 0.6915 to 4 dp. So again, that part wasn't meant to be the super tricky part. The tricky part is for part B and C. And you see part B is a probability question for 5 marks, which is, it should be illegal, but let's have a look at it. So, if we have a look at this, it says at the start of her exams, Alice put 4 new batteries in her calculator, and she has used her calculator for 16 hours already, but has another 4 hours of exam to sit. Find the probability that her calculator will not stop working for Alice's remaining exams. Now remember, it will stop working if any one of the 4 batteries stops running, it runs out. So again, you only need 1 battery to fail. Now, if we go through how this will look, I'm going to write it out in terms of the expression first so I can explain it. So we want the probability that the lifetime of any one battery is going to be greater than 20. Now, where does that come from? Well, it says here she's used her calculator for 16 hours and has another 4 hours of exams. So in total, it needs to last at least 20 hours, right? So 20, 21 hours, 22 hours, 23 hours, and so on. Keep that in mind. Now, here's the bit that is quite tricky, because I'm going to use conditional probability. Now, how do I know that it's conditional? Well, the first way is, I'm doing a bit of meta-analysis here, is they've told me she's used it for 16 hours. That has to be relevant in some way. And if you look at part A, it says find the probability that the battery will last longer than 16 hours. So, you know, it's kind of, there's a bit of a mystery going on here. But the second reason is it's conditional because the longer that you use a battery, the greater the probability it will run out in any given hour. So the way I look at it is, imagine your phone had no battery counter and you're using it. Now, in the first hour, you wouldn't expect your phone to randomly die if you know it's been fully charged. But as the hours go on, it's more and more likely that your phone will die at any moment. If you use it for 10 hours, it's more likely to die than if it was at 5 hours or 2 hours or 1 hour. So in other words, the probability changes, which means it's conditional probability. And it's given that it has already lasted for 16 hours. So we know that it's lasted longer than 16 hours already, but we want the probability that it will last more than 20 hours. So I hope that I've made that somewhat clear. To work that out, you need the probability that L is greater than 20, and you divide it by the probability that L is greater than 16. So we already know the probability that L is greater than 16 because we've already worked that out. So we can just write that in as 0.6915. The probability that's greater than 20, we can work that out nice and quickly using our calculator. If we go back, the lower now is 20. The higher doesn't change. The standard deviation doesn't change. The mean doesn't change. So 0.30857, blah, blah, blah. I might just use the answer button for that because, again, it will make my answer 8, 5, dot, dot, dot. So it means your final answer, if we go back to calculate, we have answer over 0.6915. Gives me the answer of 0.4462 to 4 decimal places. Now the question I usually get given, I get asked, not get given, when we do these kind of applied questions is that it? Because if we have a look at that, you could technically do this from here. You could jump straight to here. You've worked out one probability and you're dividing it by another probability. There's only 2 steps. And so people do ask, is that really it? The same is true with mechanics. Sometimes in moments questions, you can do 1 or 2 lines of working out and get 5 marks. The reason why they're giving you 5 marks is because it takes a lot of effort and logic and deep understanding to know that this is what you're supposed to do. So, again, just to go through it, it's already been used for 16 hours, so it's given that it's lasted more than 16 hours. What's the probability it will last more than 20? Because again, her exam is at least, or her exams plural, is 20 hours. So we want it to last more than 20 hours. And it's already last 16 hours, so it's given that it's going to last more than 16 hours. I hope that makes sense. But for part C, again, this is also quite tricky. Even though it's only 3 marks instead of the 5 marks in the previous one, I think this is also a somewhat tricky question. So, with part C, Alice only has 2 new batteries. So these batteries are completely new, okay, which means they haven't lasted any time. They are 100% full. It says show that the probability that her calculator will not stop working for the remainder of her exam is 0.199 to 3SF. So, here's the thing. We want it to not stop working, so we're looking for the probability that it doesn't run out of battery. So here's what I would do. We have 4 batteries in total. We're going to work out the probability that each of them doesn't fail. Okay? So let's just assume that we have new battery, so NB1, NB2, and then we have the 2 old batteries. Again, it doesn't actually matter the order in which the batteries are because it doesn't make a difference, right? But the idea is we have 2 new batteries and we have 2 old batteries. So the first new battery, it only has to last for 4 hours, right? Because she's already done the 16 hours of exams. She's replaced 2 batteries, so those batteries only need to last up until hour 20, so that's 4 more hours. What's the probability of that? Well, all we're going to do is for new battery 1, it's going to be the probability that L is greater than 4. And that's also going to be true for the second battery, because remember, they're both brand new batteries. That's fairly nice, that's alright. I might spread these out because the next 2 are going to be a bit longer if I'm being spoilers. Now, for the other 2, it's actually just a probability we've already worked out, because they need to last 20 hours or more, given that they've already lasted 16 hours or more. So in other words, it's just going to be 0.4462 twice. Okay, so all we need to do is work out this. So if I quickly just whip out the calculator again. Oh, man, that lagged for a second there, I got scared. Menu down to distribution. Normal CD, we have the lower bound of 4. The upper bound of, again, just a really, really big number. Sigma was 4. Mu is 18. Cool, so I get a really, really big number. That's nice. 0.99977. And that's for both of these, right? And then all we're doing is, well, we've got these 4 probabilities. We need them all to be true. So what does that mean? It means we times them all together. So we do 0.99977 squared, because there's 2 batteries, times 0.4462 squared. again, we should have 4 probabilities because there are 4 batteries that can fail. And we want the probability that each of them fails. We times them all together because, again, we want, or it's only one of them. Okay. Because only one of them has to fail, the only way that the calculator doesn't stop working is if all of them last for the rest of the exam. So we've worked out the probability that the first battery lasts until the end of the exam, it's here. The probability that the second battery lasts until the end of the exam is here. Probability that the third battery lasts until the end of the exam. Probability that the fourth battery lasts until the end of the exam. But we want all 4 of those to be true. So we want this one, and this one, and this one, and this one. When we say and in maths, what do we mean? We mean times, which is why we're doing this. So I hope that makes a bit more sense, and it gives me 0.199. So that's basically a 20% chance that her calculator will actually survive for the whole exam, which is a bit depressing, to be honest. But let's move on to part D, which is the hypothesis test. Honestly, this isn't a tricky hypothesis testing. If you've done 1 or 2 with the normal distribution, you can do all of them. So for part D, it says, after her exams, Alice believed that the lifetime of the batteries was more than 18 hours. Okay, so that means that's our alternate hypothesis. She took a random sample of 20 and found that their mean was 19.2, stating your hypothesis clearly. So again, this is very similar to the hypothesis testing from binomial. The first step is always to write your hypotheses. H0 is the null hypothesis. This is what we're going to assume to be true initially, which is that our mean is equal to 18, because that's our pre-established mean. And our alternate hypothesis, she's saying that the average lifetime should be, well, it says she believed that the lifetime should be more than 18, which means the average lifetime should be more than 18, according to what she said. She takes a sample of 20 and finds their mean lifetime was 19.2. So let's write out a normal distribution. Now, it tells us already, well, we have the mean of 18. And in terms of your sigma, or your sigma squared, all you need to do is you take the pre-existing standard deviation 4 and you divide it by the square root of the sample size. So if that sample size was 30, then it'd be bigger. If it was 50, 100, a million, whatever. And that's, of course, all squared, although we're not really going to use the squared, to be fair. And all we're going to do is actually work out what the probability, using this different method, maybe I should write this as L1 or something, using this alternate distribution that we've written, we're going to find out what the probability of it lasting longer than 19.2 hours is. Because again, we're testing if it's more than 18 hours, so we want to find the probability that it lasted more than 19.2. So just to write that out, we're finding the probability that L1 is bigger than 19.2. Just use the good old-fashioned normal distribution. CD. The lower value is 19.2. Again, our upper value is just a really big number. With sigma, typing this in, some people find it a bit tricky. You can just literally write it as it, as a division, and when you press equals, it works out the value for you. And here's 18. We get 0.08986. It doesn't really matter. Only the first kind of non-zero digit really matters because we're comparing it to 5% significance level. Because this is greater than 0.05, that means it is outside the critical region, which means there is insufficient evidence at the 5% blah blah. So there is insufficient evidence at the 5% significance level to support Alice's claim. And of course the S key decided not to press S. There we are. And that's it. For 5 marks, I do think that hypothesis testing is one of those really, really strong topics, which is quite nice. It's 5 marks even for binomial. And I mean, look at that. It's not too bad, right? And as long as you remember this part, which is some part that some students find a bit tricky, but you can just use it as an equation and that's quite nice. But yeah, that brings us to the end of that kind of difficult question. I will show you the mark scheme quickly just to show you why this was submitted in the first place. If we have a look at the mark scheme, it's not designed to teach you. So when you have something like this, it's very hard to read and it's very hard to understand unless you have a really strong understanding of the maths anyway. So I mean, maybe this would be okay, but have a look at this. I mean, the way they write it isn't necessarily the clearest. But hopefully I've gone through exactly how you'd approach a problem-solving question like that. it is very difficult in A-level maths, far harder than GCSE maths, because it requires some level of logic or like real world experience to kind of understand what's going on. But again, with practice, you should be very, very fine with that. But I'll leave you to your revision. I'll see you in the next one.